Hey everyone, we're going to go ahead and get started. Thank you all for showing up this morning to the SSC Chem 1311 Exam 3 review. My name is Jeffrey and I'm a PLTO leader for Gen Chem, and this morning I'll be your host leader for this session. So if this is your first review session from the SSC, we're going to have a lecture portion followed by breakout rooms with practice problems led by the leaders. So if you have a question at all during the lecture period, feel free to type it in the chat and then one of the supporting leaders will get to you. I've also included a QR code to the slides here, so in case you want to have your own copy, if you want to take notes on your tablet or whatever, then you can go ahead and do that. But we're just going to go ahead and just get started. First, we're going to go over Chapter 6, which is the first chapter on your exam, and that's going to be about representing molecules. Chapter 6 prefaces you with the covalent bond formation graph, where the x-axis is the distance between atoms, and then the y-axis is the potential energy. So first, before there's any type of bond, there's going to be a high amount of potential energy right here when they're like super close to each other, and then this will go down right here, and then this area is going to be your repulsion. Next, the potential energy will increase until there'll be a lot of stability between the bonds when there is attraction. The basis of bonding can be also compared to electronegativity and polarity, where electronegativity is that certain elements have a tendency to draw electrons more to them than other elements. If you remember from the last exam, there was a trend called electronegativity that increases. Usually, it's really high on the top right. So this is kind of what the basis of bonding is. So we measure this degree of electronegativity by the polarity and dipole measurements. So when there is a significant unequal distribution of electron density in a compound, it's said that the bond is polar. And polarity is the measure of the difference of electronegativity in a compound. And this is denoted by the dipole vector in this example up here with the HCl. So notice how there's going to be the pointing arrow where it's going to be more negative to the that's more electronegative than the H, and H is denoted by the little cross right here. On the other hand, there are something called nonpolar bonds, and this is going to be insignificant difference in electronegativity. This is usually a bond in the diatomic molecules such as Cl, Br, H, and CH. Even though you may think that there's a difference of electronegativity, when you're measuring it, it's super insignificant, the numerical value itself of electronegativity. So we can just go ahead and just call them nonpolar. We have another measure called percent ionic character, and it's the amount of electrons sharing between atoms in a compound, and it's based on the degree of electronegativity. So usually you'll see this in a typical ionic compound where you'll have the electronegative nonmetal and then the not so electronegative not metal, excuse me, and then they'll have the measurement of percent ionic character. So the basis for bonding is called the octet rule, where the valence electrons or the electrons of the last shell of each element want to either lose or gain electrons to maintain 8 electrons of the ring for max stability. In ionic compounds, this usually leads to metals losing and then nonmetals gaining. Well, why? If you notice, the nonmetals are usually pretty full of electron shells. They usually have around like 7 or 6 valence electrons. So it's easier for nonmetals to gain 2 electrons compared to lose 6 or 7 in order to completely remove that shell to get 8. On the other hand, metals have usually 1 or 2 or 3 even electrons, so it's easier for them to just lose those 1, 2, or 3 or remove or gain 5, 6, or 7 electrons to get that shell. And usually in covalent compounds, you can kind of see that they share electrons instead of giving them. And so these sharing will always result in 8 electrons of a ring. We represent these schematics of bonding in elements in the Lewis structure, and essentially it's a representation of covalent bonds in which the electrons of pairs are shown as dashes or pairs of dots between 2 atoms. The lone pairs are shown as pairs of dots on individual atoms, and only the valence electrons are shown in a Lewis structure because these are the bonds that are involved in bonding. And so we're going to go over some few tips to kind of draw them. So this slide is pretty hectic, but it's just kind of a skeleton on like how you can kind of draw the structure. And this is one of those topics where it's easier to just learn how to do it by doing. So we'll go ahead and practice more of those in the practice problem session. So with the first step is usually you want to count your number of valence electrons. For polyatomic ions, you add the electrons to the number to account for the negative charge, because with negative charges, that means that you gain an electron, right? So it kind of makes sense why you have to add more electrons. And then subtract electrons to the total number to account for positive charges. So if you have like a positive molecule, you will want to like, if it's a positively charged polyatomic ion, that means that it has one less charge, so therefore one less electron. For the molecular formula, draw the skeleton of the compound using chemical symbols and placing the bond atoms next to each other. In general, the least electronegative atom will be the central atom. This is kind of will be pretty kind of straightforward if you kind of see it. So usually in a Lewis structure, you'll have one type of atom be surrounded by other ones, and so with practice you can kind of see which one will kind of go in the middle. And for unclear ones, if it's kind of not clear where, usually the least electronegative will be the central atom. Next, you draw a single covalent bond, a dash, between the central atom and each of the surrounding atoms. So this kind of denotes a bond where 2 electrons are shared. And so that's transitioning to number 4. For each bond or dash in the skeletal structure, you subtract 2 electrons from the total. And this is because each bond is made up of one electron and another electron. Now, step 5 is determine the number of remaining electrons. And if any electrons remain after step 4, place them on the central atom. But the thing is, number 7, if the central atom has fewer than 8 electrons after completing steps 1 to 5, then you have to move one more pair from the terminal atom to form multiple bonds between the central atom and the terminal atoms. So this is essentially meaning that you're forming single or triple bonds, because if there are no more electrons you can't work with, then what you have to do is you have to borrow them from other elements. So I have a little schematic here that shows the length and the number and strength of a single, double, and triple bond. And usually, if you see here, as the number of bonds increase, the energy increases, right? But then the length decreases. So if you see here, one single bond is going to be like the weakest, right? Energy. It's 347 kilojoules per mole compared to the other higher amounts of energy, but it also has the highest length. And why is this? Well, you can kind of think of it as if you have more energy for a bond, that means that those bonds are very close to each other. And so the reason why it's so strong is because the force that the electrons exhibit on each other are going to be really close to each other because of their strength. So usually as the number of bonds increase, the energy increases, but the length decreases. So here are some exceptions to the octet rule. First, you have the expanded octet, and you find this in blocks 3p or below. And the reason why we have the expanded octet is because below the 3p we have something called the transition metals, and so the transition metals have those inner core electrons that we have to account for. So notable exceptions are beryllium, boron, where instead of the usual octet, you kind of just want beryllium just wants 2 bonds and the boron wants 3 bonds. It kind of makes sense because the good way I like to remember is that beryllium is in group 2, so you just want to draw those 2 like dashes on them, and then boron is in group 3, so you just want to draw those 3 dashes on them. And next you have the odd number of electrons. This is kind of rare, but you kind of find these in called radicals, and they will not have a pair. So next, we'll go over how to calculate formal charge. The formula for formal charge of an element is that it's the element's valence electrons. Usually, if this is in a group number, so let's say like group 6 has 6 electrons in it, minus the electrons on the element, so the number of individual electrons minus the number of bonds dashes it has. So the example I have here is that if you look at this S in the middle, the valence number like S has in the periodic table is from 6 because it's in group 6. And then you'll count the number of lone electrons it has, which is 0, right? It doesn't have any electrons on it. And then finally, you count in the amount of bonds it has. So it has 1, 2, 3, 4 from the 2 double bonds, and then 5 and 6 from the single bonds. So if you take the group number 6 minus 6, you'll get the formal charge of 0. So that has that S has a formal charge of 0. On this bottom oxygen with the double bond to it, well, we know that oxygen has 6, is in group 6 as well, so it has 6 for the first part of the equation. Then we have 4 individual electrons, so we can say that it has 4 for that. And then we have 2 bonds on it, so the formal charge is 6 minus 4 minus 2, so therefore that formal charge is going to be 0. On the left, however, those left oxygens, the group number is still 6 for oxygen, and then it has 1, 2, 3, 4, 5, 6 lone electrons minus 1 bond. So the equation for formal charge is going to be 6 minus 1, and then the formal charge for that is minus 1. And so you can kind of see the math done over here for you. So why do we find formal charge? Well, since elements in the 3p or below can have multiple bonds on them, so they have that expanded octet, sometimes you may be asked to find the best Lewis structure. Like, all of those are perfectly valid. So a Lewis structure can have many Lewis structures. A compound could have many Lewis structures, but sometimes they're not like the best, or they're not chemically favorable. And we're going to go in and explain like kind of why. So here are some of the guidelines for the best Lewis structure. So you want to minimize the charges. So you got to keep them kind of to a minimum. So for instance, instead of having a formal charge of +4 on an element, you kind of want to spread them out. So say +1, +1, +1, +1, because I like to think of it as that it's very concentrated on one of those elements. So you kind of want to kind of keep them out, spread out. Like I mentioned, like spread out the charges, avoid clustering a big charge value to 1. And the placement of a plus or minus polyatomic. So usually when you have polyatomic ions, they have a charge carried to them, and then one element will carry that charge. For example, nitrate is NO3 minus, so something has to have the minus. And so the guideline for that is, so more positive charges go on the least electronegative atoms, and then the more negative charges go on the more electronegative atoms. And that kind of makes sense, because electronegative means that they want more electrons, and so if you want more electrons, it kind of makes sense where you have to put that negative charge, because that's where the electron is. Conversely, if you have a least electronegative atom, then that means that it's more positive, because it doesn't really want all those electrons, so it wants to stay, positive. So therefore, it kind of wants to go on the least electronegative. Okay. So we're going to go ahead and talk about resonance and bond order. So going back to the structure of nitrate, notice here there are three Lewis structures here, and they all differ in their location of the double bond. And so notice how these double bonds, they can kind of exist in 3 different locations. So for here, you have the double bond on the right part, the double bond on the left part, and the double bond on the top oxygen. And so these are all kind of valid. And the reason why this happens is because these are essentially delocalized electrons that are traveling through in alternating positions. So there's not necessarily at one point in time at these locations. Rather, at a given point in time, they're all cycling through those forms. And we call this by resonance. And the reason why we can kind of see that these resonance structures are valid is because we can calculate something called the bond order. And the bond order is the bonds the central atom has over the number of shared atoms it has. So for example, if I take a look at the central atom here, the nitrogen, it has 1, 2, 3, 4 bonds to them. And then for the shared atoms, it has the 3 oxygens. So the bond order will be 4 divided by 3. So therefore, if you calculate the bond order for all of these 3 of them, they're all going to have the same bond order. And we can kind of see that all resonance structures are therefore valid for all these structures. That was chapter 6. And then we're going to go ahead and move on to chapter 7, where we're going to talk about molecular geometry and bonding theories. So the big basis for the So for the bonding theory is that there's going to be the repulsion of the electrons in the atoms to minimize the difference between them. So the lone pairs, they cause repulsion, and so when these lone pairs on the Lewis structure, they are present, they'll go ahead and kind of rearrange themselves into a shape, and so the molecular geometry, a shape that accounts for the lone pairs. So the molecular geometry is the shape that accounts for the lone pairs using Vesper theory. So that means that when you're looking at the shape, you're looking at the number of like lone pairs there are as well. On the other hand, there's a difference called the electron domain geometry, and it's a shape that does not account for the lone pairs that are based on electrons of electron density. So what that means is that let's say the 4 lone pairs right here, instead of just looking at this as 4 lone pairs and trying to find the Vesper shape for 4 lone pairs and 2 atoms, what you're going to do is you're going to look at the area of electron density. So instead of thinking about that it has 4 lone pairs and 2 shared atoms, you're going to think about it as there's just 6 areas of electron density. And we'll go into more detail about what that means later on. But for now, well, how do you get these shapes? Well, if you look at the little arrow I drew here, so to get the Vesper shape, you have to know the Lewis structure. Notice how everything kind of builds on by itself, because when you find the Lewis structure, you can look at the central atom and then find out the shape that corresponds based on whether you're asking for molecular geometry or electron domain geometry. And I have more information about that one here. So you have to know the chart. I know this is a lot of memorization, but the tip that I can give you is that think about it as the amount of electron bonding groups and lone pairs it has. So for example, if you look on the chart, we have the electron groups 3, right? Think about it first as electron groups, but then think about it as in like how many bonding groups and lone pairs there are. So that means for the electron group, I have 3, and also have 3 bonding groups, so 3Bg plus 0 lone pair. And then moving on, I have 2 bonding groups plus 1 lone pair. They'll give you 3 electron groups, and then give you the corresponding shape. So one thing I like to point out is that notice how the electron geometry is kind of the same. It kind of repeats. And why? Is because the electron geometry keeps into account only the areas of electron density. And that could be a lone pair, or that can be a shared atom it has. So in this example, notice that this BCl3 molecule, it has three areas of electron density. So what's going to happen is that Vesper says that all these groups are going to repulse to form a shape that's trigonoplanar for the electron geometry, but then it's also going to be trigonoplanar for the molecular geometry because there are lone pairs. However, if you move on to here, the next shape, notice that the electron geometry is still the same because we're still working with 3 areas of electron density in this SO2 molecule, because we have this oxygen and this oxygen, which are 2 domain groups, and then 1 lone pair, so 2 plus 1. And then what's going to happen is that when you're taking count of its lone pair, you're going to get a shape called bent. And so when you have a presence of lone pair, they'll shrink the angle because those lone pairs will want to hog up a lot of space. So it's going to like have everyone like part, like the other elements part ways. So if you see this lone pair on the S molecule, what's going to happen is that S is going to occupy more electron density. So it's going to go ahead and pull down the double bond and then the single bond down. So that's why the angle between the O and the S right here is less than 120. So I would recommend doing what you need to do, making Quizlets or drawing the shapes out. You really need to know this. This is really important for your exam. Know the electron geometry, the molecular geometry, the bond angles, and then kind of a sketch too, if that helps you. So the trigonal bipyramidal electron geometry is unique is because there are 2 different types of angles you can get. So one of them is the equatorial angle, which is going to be based on the equator, so like right around here. So like if you think about equatorial equator, it's going to be near the equator, which is like this. It's just a better molecule that's here. And then axial is going to be between this one, the Cl, the P, and then the Cls. So you can kind of see it roughly forms a 90-degree angle. Sometimes you'll see on 3D models, there are going to be dashes or like solid lines. So the dashes means that it's a wedge, so it's coming out of the plane, and then the dash will come out of the plane, and then the wedge is in the plane. That's kind of what it means. So here's another example of how electron domain geometry differs from molecular geometry, where electron geometry is account for the areas of electron density, right? So notice how we have the 4 pairs of electrons require 4 electron orbitals to orbit. So therefore, it's going to be the tetrahedral arrangement of electrons. However, with the molecular geometry, you account for the shape of the lone pair repulsion and then also the shear atoms. So in this case, still 4 areas of electron density, right? But the thing is, because there are 2 lone pairs and 2 shared atoms, we have the shape called bent. So on your exam, it's really important for you to differentiate between whether or not the problem is asking you for electron domain geometry or molecular geometry, because if you put molecular geometry for a question that's asking you electron domain geometry, you will get the problem wrong, and vice versa as well. So it's important for this test, I mean for any test really, but for this one to really read the problem. Next, we'll talk about the deviations from the bond angle. So lone pairs and more than one type of bond exhibits more repulsion, needing more space. So if you look at the example down here, we have a C double bond to 2 H's. And so what's going to happen here is that usually if you look at VSEPR, you predict that since there are three areas of electron density, so if we look back to the chart, that corresponds with, if we have 3 bonding groups in 0 lone pairs, that's trigonoplanar. So for here, in a trigonoplanar group, you expect every degree to be 120 degrees. However, if you look at this bond angle right here, the 118, it's less than that. And why? It's because that there are double bonds, so they're going to exhibit more electron density, and so they're going to repulse more. So in order to account for that space, what's going to happen is the other bond angles are going to like part and shrink, while this one takes up more. So the C double bond O angle would be greater than 120, and then as a result, this one will be less than 120. And so here's kind of a little diagram to see like how much repulsion there is. So more repulsion is in the lone pair, in the triple, and in the double. So when we have the shape, we can also go ahead and predict the polarity as well. And so when you kind of draw this molecule, what you can do is you can kind of show the net dipole vectors that we did earlier. And so these electronegativity vectors, since vectors carry magnitude and direction, they can kind of cancel out. So in this example, like the first one, BCl3, notice how BCl3, once you draw the Lewis structure, you'll get the BCl3, but with no lone pairs in each one. So therefore, if you have 3 areas of shared atoms or electron density and no lone pairs, it's going to correspond to a trigonoplanar shape. So in this trigonoplanar shape, if we draw the molecule out and we draw the vectors like so Cl versus B, Cl is more electronegative because of our electronegativity rules. So drawing that arrow out, these arrows kind of cancel out. Because why? Well, it kind of doesn't seem obvious here, but sorry. If the BCl on the left and the BCl on the right, what's going to happen is that those vectors are going in the same direction. So when you draw the resultant vector, it just goes straight down. So the resultant vector from those 2 vectors on the left and the right, they'll go straight down. And notice we have an opposing vector, the BCl equal magnitude, on up here, so they'll cancel out. So it's really important here that you kind of look at it like 3-dimensionally and see which vectors cancel out, but also whether or not they're the same magnitude or not. Because sometimes that if the top Cl was kind of another element, let's say, I don't know, like fluorine, that electronegativity difference would differ. And so you're comparing the BCl electronegativity vector to the BF vector. And so we know that F is more electronegative than Cl according to the periodic table, and therefore there would be imbalance there. So then that wouldn't cancel out, if that makes sense. Here are some other examples. You can kind of like, try to draw these on your own and kind of test them out. But the main takeaway is that you draw them and then you kind of see which ones cancel and which ones don't cancel. So sometimes the molecule could have polar bonds but being overall nonpolar, and this is kind of a confusing topic for students. And the reason why this is so is because we'll be drawing these vectors out. Because notice how in the first example, we all have polar bonds here, but how they cancel out to overall give a nonpolar or non-charged, non-dipole movement molecule. Okay, so next we're going to talk about the intermolecular forces. There are three really big ones that you should know. London dispersion is just the electrostatic attraction between two elements. And this is present in all molecules, so including the nonpolar ones. Dipole is made up of the force from the polar bonds, and it's present in polar molecules, but it also consists of London forces. So if you have if you have a compound that has a dipole-dipole force, it also has a London dispersion force. So hydrogen bonding is force made with a hydrogen with the elements F, O, and N because of their high electronegativity differences. And if something has hydrogen bonding, it also has London dipole and as well the hydrogen. And I can kind of show you, like, I made a little schematic here where H bond is like the most like specific, but it has like all three of them. But the London ones, it's very broad, but it doesn't encompass the other two. So it's kind of a little schematic that I like to know. So if you have a question that asks you like what forces are present, if something has H bond, a hydrogen bond force, it also has dipole and London. However, if something only has London, then it pretty much only has London, and this is from nonpolar molecules. And how do you find whether or not something is nonpolar or polar? Well, you kind of go back to here. You first draw the Lewis structure, and then you determine the 3D shape, and then you draw the electronegativity vectors, and then you're going to see where they cancel out. So notice how everything kind of builds on top of each other. So it's really important that you kind of like build the solid foundations, because you'll see this again in your other chemistry classes too. So intermolecular forces also affect solubility. So like dissolves like, which means that nonpolar elements dissolve in other nonpolar substances, and polar substances dissolve in other polar substances. So this is because if you have, let's say, something that's very polar, and let's say water, for example, because you have like that negative from the OH and then the positive from the H, right? Those elements, what you're going to do is that it's able to dissolve the like other elements such as like ions or ionic compounds because of that like charge, like dissolves like. Okay. So we'll transition to line diagrams, and this is essentially just a shorthand notation to make the carbons and hydrogens less repetitive. You don't see this a lot in general chemistry. You kind of only get introduced to it, but in organic chemistry, this is kind of the notation used because you'll only talk about carbon compounds for organic. And so just to make it easier on like the scientists and when you're drawing them, these little points, the junctions, I would say, are the carbons. So notice how on the first molecule we have a C, 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 C here, and at each edge it corresponds to that C. And just because it's empty here doesn't mean that there are other elements present. So we know that carbon has 4 valence electrons, so that means that naturally it will want to form 4 bonds, and so that's what happens with hydrogen. Hydrogen will go ahead and connect with any carbons you see, so kind of just get used to that right now. Any carbon you see will have 4 lines to them, and some of the lines will be hydrogens. So in this case, the first example, notice that we already have one from the carbon left to right. So from the first carbon, there's only one type of bond present, and that's with the other carbon bond. So therefore, we need to fill the other 3 bonds, right? The other 3 bonds. So we're gonna put just H there. And even though there are H's present here, it's not shown on the skeletal or the line drawing. So a good pro tip I can give you for your exam is that when you see a line skeleton, just like start drawing the H's, because we're gonna count something for these, and they can get really annoying when you don't label all of them. A common mistake is students just don't label them, so they're just like, oh, this is this is just the molecule, so they just don't account for the hydrogens, but they are there. Double bonds, they're denoted with like this one right here. Notice how there's a big web of H's as well that's not shown, and then there's also other groups that you can show here. So this is what we call a ketone, so it has like other carbons, and then a double bond O. Okay, so it's pretty much that slide. We're going to talk about the different bonding theories. The valence, for the first theory we're going to go over is the valence bond theory, and essentially the overlapping of the orbitals. So the first example I have is that the H and the H, they kind of overlap to make the HH sigma bond. The second one is the HF. So you see that they overlap to create the HF sigma bond, and then those p orbitals in the F overlap to create the FF like sigma bond. The more prevalent, I would say, theory is the hybridization theory. And so this theory is a little bit complicated to explain, but essentially what's going to happen is that first you have the ground state of carbon and it's going to promote itself. So notice how if we don't, just ignore the 1s here. So notice how we have a 1s, right? A 2s that has 2 electrons in it, and then a 2p. So what's going to happen is that one electron, that one arrow from, let's say the down arrow, we're going to go ahead and we're going to move that over here. And so this is going to be called promotion. So the promotion value, the promotion element is called C star, which is a C star here. And so now we have formed different orbitals where we form specific hybrid orbitals. And then so these orbitals will go and interact with the other orbitals to kind of make a combination or mix of them. So here's kind of an example here. We're going to go over shortcuts, but essentially you will always kind of have these a total of 4 orbitals because those are the orbitals that are promoted, that were involved. So we have like the 3 original ones, and then we have the promoted one, which is like that guy. I hope that made sense, but this theory is a bit tricky to understand, but just kind of know that the elements, especially carbon, will kind of promote, and then this promotion will cause a mixing of orbitals. And so those open orbitals, since they only have 1 electron on them, like notice with the 1 electron here, other elements can go ahead and mix with those. We also, from this theory, we also have something called sigma and pi bonds. So pi bonds are prevalent in the double and triple bonds. Where you see here, there is a pi bond, like in this. So when there's a C double bond C, right? In double bonds, there's this empty like orbital called the pi orbital, or the pi orbital. And so what's going to happen is that electrons are feel free to like move into there and kind of form that double bond. And so usually in this diagram, the hybridization, you draw it, you're going to have a pi bond and then a sigma bond right there. In triple bonds, however, as you can see here, there's going to be a C triple bond C in this molecule. You have 2 pi bonds, and then there's going to be 1 sigma bond with the orbital. This is confusing, but I can kind of just give you like a hint. So usually what you want to take away from this is that the sigma and the pi bonds, each single, double, and triple, this should say triple, I'm sorry it doesn't, but single, double, and triple, they all have their own sigma and pi bonds. So all of them have 1 sigma bond, and the pi bonds kind of differ. So the single bond has 0, the double bond has 1, and the sigma bond has, the triple bond has 2. Okay, yeah. And so in your problems, they're going to give you these instructions that are going to be like, oh, count the number of sigma and pi bonds that's going to happen, that's going to be in the presence of the molecule. So you have to account for each single bond in the molecule. So you have to go and count all of these molecules, the sigma ones, and then count all the ones for pi. So these problems are they're just very tedious, so I would save them for the last exam question that you do. But most importantly, do not forget to count the hidden hydrogens. What I mean is, if we go back here, notice how, say, sometimes they'll give you like the skeletal or line drawing, right? But then if you say that it has a 1, 2, 3, 4 sigma bonds, that's going to be wrong because you do not account for the other H bonds here. So you have to account for those as well. So it's very tedious, and sometimes you miss one. So I would recommend for you to do like the last question. Okay, so that was pretty convoluted in terms of hybridization, but here's kind of a shortcut that I can give you. So all you have to do is just count the amount of like groups on the element. So for example, if I wanted to find the hybridization of the N here, so I notice that there's one area of electron density, the triple bond, and another area of electron density, the lone pair. So you just count sp, right? Because that's going to be sp hybridized. If you have 3, you just keep going, sp, and then you add another p, that's sp2, right? Because 3 areas of electron density. And then 4 groups, if you have sp3, it's because s, and then you have a p, and then you have a p, and then you have another p. And so here's kind of a shortcut here. So if you have two regions of electron density, you'll get sp shape, 3, sp2, 4, sp3. Since we move on, we fill all the p orbitals. We're going to go ahead and fill out, I got a d, and we're going to sp3, d2. So sometimes you might have an exception. If an atom looks like it can actually be sp3 hybridized, but is able to like resonate, so you can draw resonance structures, it is actually like an sp2. So this accounts for the empty p orbital, because remember a few slides ago, we talked about how resonance, it's always at one point all the electrons are just cycling through or oscillating. Well, it can that's the reason why the hybridization is a bit different. So if you look at this right here, that N on that lone pair on the N will actually resonate, and you can actually put like a double bond on the O, on the N, I mean, and then just have like 3 electrons on the O if you draw the resonance structure. So instead of saying that it's sp3 hybridized, because if you look at it right now, it's going to look like S. That lone pair is going to be S. The 2 H bonds are going to give for 2 P's, and then the carbon here will be another area of electron density. So you have sp3 hybridized, and therefore it would look like you think that it looks like sp3. But if you draw the resonance structure, if that double bond was on the NH2 and you count the area of electron density after that, which would be 3, that would correspond to sp2. And here are some kind of other examples that I've listed out. You can feel free to draw the resonance structure for practice and see if we can kind of understand why there's sp2. Okay, so thank you all for kind of listening through that lecture. So now we're going to go ahead and take a quick break, and we're going to go ahead and work on practice problems after like a 5-minute break, so 11:45. If you all want to like kind of quickly scan the problems or kind of print them out at home or upload them to your tablet to work on as well, you can go ahead and scan this QR code and upload it. So I'll see you all in like around 5 minutes, and then we can go ahead and get started. Okay, y'all. We're gonna go ahead started on the practice problem portion of the review. So I'm gonna go ahead and kind of work through this out with you all. So feel free to follow along and work on at home. But if you have any questions as I'm kind of working through the problems, feel free to ask in the chat or unmute yourself and ask. Okay. So let's go ahead and take a look at the first problem. So this first problem, there's a lot of parts to it. So we were asked to fill out this chart, and this chart gives us a bunch of compounds, and then and so there are compounds, and so what's going to happen is that we're asked to find the Lewis structure, the 3D model, the 3D model of it, the molecular geometry, the electron dynamic geometry, hybridization, IMFs present, and then non-polar color. So it's a long problem. It's a long problem if it's only one problem, but we're going to go ahead and just work through it out. Okay, so the first step of any problem regarding any of these problems is just to count the electrons, right? So you want to like count the electrons that you have to see how much you have to work with. So on this one, right, you have 5 plus 3, or third table, which is 8. And so the next step is you kind of want to draw your skeleton, right? P, and then you want to draw kind of like the other elements surrounding it, H, and then H. Okay. The next step is kind of want to draw the single bond, right, to connect all of them. Okay. And then subtract the single bonds, the amount of electrons they use from the total amount. So we use 2, 4, 6. 6, so 8 minus 6, we have 2 left over. Okay. And then if we have 2 left over, that means the 1 is right here. Okay. So next, we can kind of want to draw the 3D model and we show their angles. So according to Vesper, I'm going to give you a hint. For this problem session, if you haven't memorized the shapes already, then that's okay. I would pull out that slide that I posted and then kind of have that chart ready as we're working on these problems together. So P, and then the angle would kind of look like this, and then this. That's kind of the model. And so if we have something that corresponds with 3 electrons and 1 lone pair, that lone pair is going to repulse, and this angle would be less than 109.5. And why less than 109.5? Well, we have 4 areas of electron density, right? So that would kind of correspond to the trig pyramidal molecular geometry. I'm sorry, the tetrahedral, right? The tetrahedral electron domain geometry. But the thing is, in order to account for the electron lone pair, we have to go for that and think about the repulsion of the lone pair. So usually in tetrahedral, this is going to be 109.5, but because there's a presence of a lone pair, it's going to make these angles less than 109.5, because these guys will take up more space. So going back, the molecular geometry, the way I like to think about it is that it's 3 shared atoms plus 1 lone pair. So if you look on the chart, 3 plus 1, or 3 atoms plus 1 lone pair, that corresponds to trig or pyramidal. Let me go ahead and see if I can like kind of figure out my tablet board. But I could just type it. Okay, so that's trig pyramidal. So the electron domain geometry, we just count the 4 areas of electron density. So that's the H, the H, the H, and then there's also a lone pair, but that's not a lone pair when we're talking about electron domain geometry. We're just more concerned about areas of electron density. So something that corresponds with 4 areas of electron density, that's going to be tetrahedral. So I'm going to say tetrahedral. And then our next question is predict the hybridization. Okay, so if we remember from hybridization, all we got to do is just count the domains. So we go S right here, S, then we go P, and then we go another P down here, and then we go another P down here. And so the hybridization would be S, P, and since we have 3 of them, it's 3. Okay. Any questions on that? No? Okay. If there are no questions, then we can just move on. So next is the IMFs present, right? But to determine what intermolecular forces are present, we gotta take a look at the polarity of it. So if we look at the polarity of this vector, right, if we kind of draw it, I'll go ahead and redraw the molecule just because it looks kind of messy down there. So we do P, right? We do H. So what's going to happen is that these 2 H's are going to make one big vector here. And then that pointing that way towards the P, and then make another vector to that P. So notice how these 2 vectors, the resultant ones, they kind of cancel out. So we can say that this is nonpolar because there is no net charge. Okay? So any IMS present in nonpolar molecules, if you remember, it's just going to be the LDF. It's not the dipole-dipole because that requires a polarity, and this is a nonpolar molecule. Great. Does anyone have any questions? So if not, I'll let you all I'll give you all a few seconds to try the next one, and we can come back as a main group and talk. Okay. Anyone have any questions on that?
I think someone was asking why is pH3, why is that nonpolar? Because it has that
Sure.
one.
Okay. Okay, sure. Yeah, we can go work on that one. So give me a second. Let me go ahead and just like kind of quickly calibrate my Wacom board because it's kind of like lagging a bit. Sorry, you all. Okay, so I fixed my Wacom board and yeah, okay. So, okay, yeah, I think there was one mistake I kind of made. So instead of a bench shape, it would be, instead of a, like this shape, it will actually have this is actually, it will have the bench structure due to the electron pair. So instead of like this shape, it would be bent. And so that bent will be the non-polar. I mean, it will switch to polar because if we quickly go ahead and draw it, that is a good question. So we do like this, right? It's bent. So those vectors, they won't cancel out. Yeah, and that's correct. So this is going to be polar, and then the forces are going to have the dipole, 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 dipole. Okay, yeah, good catch. Okay, so going back to the next problem there, what's going to happen is that we're going to have the BRF5, right? So as I mentioned, I've drawn over here, I've drawn the structure, and then I've drawn each lone pair, and then there's going to be one lone pair on the BR. So what's going to happen is that we're going to draw the shape, right? So the shape will kind of correspond to like something like this. And so because of this propulsion, usually this is what, 1, 2, 3, 4, 5, 6, 6 areas of electron density with the 5 fluorines and then the 1 lone pair. And so what's going to happen is that usually it's going to be, if you have 6 areas of electron density, it's usually going to be, what, 90 degrees? But because of that lone pair, we're going to say that it's 90. Okay, and so with the molecular geometry, what's going to happen is that it's going to go ahead and correspond to square pyramidal because of the shape. And then the electron domain geometry is just going to be the areas of electron density, so it's going to be octahedral. Octahedral, and then hybridization. If we count all of them, so it's going to be, if we count the electron domain density, it's going to be S, P, 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 D, and then another D. And then so therefore it's going to be SP3D2. Polarity, if we draw the vectors, we draw right here, then one right here, and then right there, and then right there, so that connects to all the F's, and then we have one on the top, and this is going to be the odd one out because there's nothing to cancel down here, so therefore we can say this is going to be polar. So what forces correspond to polar? We have LDF and dipole, dipole, dipole. Okay. Cool. So go ahead and let's go ahead and just erase that. These little marks right here. Okay, cool. So I'll give you all like a few seconds to work on XCFE2, F2, and then we can go ahead and get started. Yeah, so Michael, that's a good question. So you kind of have to memorize where the the so for that one, I guess the only tip I can give you is that you kind of have to memorize where they kind of go, because if you look at the model, it's kind of looks, so those wedges and dashes kind of show you where it's coming out, what's coming in and out. So those wedges and dashes, they're kind of placed there only to kind of denote like this is what looks like on a 3D model. So I can't really like kind of give you like a tip, but if you look at the model on the sheet, then it kind of tells you how. And yes, there was a bit of an error with the key. Thank you. So it's actually going to be trigonal pyramidal, like was mentioned, because it's polar because the lone pair pushes the hydrogens down, creating the pyramid, and then the resulting vector would be pointing up. So just to make a little correction to the key. So um, it's trig pyramidal, that's correct. But what was wrong was that this was going to be polar. Yeah. So polar, and then it's going to be dipole dipole for the IMFs as well as LDF. Yeah. Sorry for that correction. Okay, so let's go ahead and draw the structure for XCF2. So we're going to go ahead and do that. So counting the electrons, right? So we have XF2. So if we go ahead and count that on the periodic table, let's see. So XE has 8, and then we count the 14 from XE. I mean F, the two Fs. So XE and then F and then F do the kind of structure. And then we label the electrons as needed. So label them here, here, and then here. And then we do here, and then here, and then here. Right, so we have 3 lone pairs, 2 and 2 of the shared atoms. So if we draw the shape, it kind of looks like this. And then we do this right here, and then we do that. So according to the shape, it would look like kind of linear. So according to the molecular geometry, it would look as a linear model. And then the electron domain geometry, we just account for the areas of electron density. So since there are 5 areas of electron density, it's going to be trig bipyramidal. Bipyramidal. Okay. And then hybridization, you just kind of count the electron domains. So we have S, P, 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 and then we also have P, 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 and there. And then that would be, hybridization is going to be, let's see, S, P, 3, and I think there's just 1D. So, and since it's a linear model, that vector goes on there, that vector goes up here. So it's going to be a nonpolar, because those cancel out. And then that's going to be LDF, since it's nonpolar. Okay. Now we have this molecule. We have C2H4. What's going to happen is we're going to do here, just draw the kind of skeleton. So usually for these molecules, you have the 2 H's together, with the 2 C's together. And then if we count that, it's going to be for 8, 12 electrons, right? So how many did we use? We used 2, 4, 6, 8, 10. right? We use 10 of them, so we have 2 left over. So if we put 2 here, notice that we don't have any more electrons, but that octet for C isn't satisfied yet, so we gotta draw this, and we're gonna put it over here. We have to make a double bond now. So for each carbon, we can actually go ahead and find the shape. So if we draw the first one, it's gonna look like the first carbons connect to the second one, and then just connect to H. And it kind of repeats because they're both the same. They have the same spatial arrangement. So the angles, you think that it'd be 120 because that's what corresponds to 3 electron domains, but it's actually going to be just greater than 120 because of that double bond. And we know that double bonds take up more space because of the electron density. Okay. And so both carbons are going to be trig planar because that is the electron domain with the 3 electron densities, right? And well, the electron density is the same here as molecular geometry because there's no lone pairs, so both of them are going to be trig planar. So hybridization, if we just count them, it's going to be S, 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 V, S, V, 2. And so I kind of want to give you all a second to like kind of figure out like what kind of the polarity it is. So I'll give you all a second to do that. So for this one, to determine the polarity, you can kind of have to like kind of look at it as an overall picture. So going back, let's kind of draw the picture right here, right? H, right? So if you draw those vectors, it looks like this, it's like this, and then it's going to point to the more electronegative one. So this one will cancel this one out, and this one will just cancel this one out. And so that will give you the nonpolar. So you nonpolar because there are no charged molecules. And then IMFs, you just get LDF. It's just nonpolar. Any questions on that? All right, cool. If there are no questions, we can go ahead and give you a second to work on the next problem, and then we can talk about it. Okay, so let's go ahead and take a look at the next problem. So we have NO, right? The way you want to start off this problem is that you want to kind of just count out the electrons like usual. So we have nitrogen, I believe, has 5, and then oxygen has 6, and then we subtract 1, which will give you 10, right? We subtract 1 because of the plus charge. So drawing that, we have N, then connect up O, so we have minus 2, so that's 8, and so we just go ahead and start filling them out. So 2, so 2, 4, 6, 8. So I would recommend putting them on the electronegative one first, so that'll be O. So 2, 4, 6, 8, 2, 4, 6, 8, 10, right? So notice how there is, we kind of have to share them because there is no more electrons, but we need to complete the octet. So we're going to share like that. And then kind of draw that plus here. Okay. Now we're going to go ahead and draw the shape. So if it's just an O, that's going to be a linear model. It's going to be 180. Because just two areas, just like there's 2 areas. Molecular geometry, that would be linear because it's just those atoms, and then linear as well. Hybridization, we just count density, so that would be S and P. S and P. So to determine whether or not it is electronegative or it's polar nonpolar, well, notice how N and O have different areas of electronegativity according to the trend. So it's going to be polar. And polar, it's going to correspond to the F and then the dipole. Cool. Any questions on that? Okay, so let me go ahead and just erase this work, and then we can talk about the next problem. So this problem is asking us to rank the following bonds in order of increasing ionic character. So what's going to happen is we know that ionic character is another measure for electronegativity. So if we kind of see what's going on here, we have all these H's, and then we can rank them in terms of electronegativity with these three guys, right? So we know that fluorine is the most, right? And then this one's the second, and then this is the third. So increasing ionic character, since this has the most electronegativity, the F, it's gonna produce a greater difference. So we can say that that's the most. And then we have Br, the BR-H bond, and then we have the CH bond.
Jeffrey, there was a question about the NO molecule, about why that was polar.
Oh, sure. Okay, so that's a good question. So NO, right? So if you look at the periodic table from your trends, notice how O is more electronegative than N. So there's a dipole going this way, and that's going to be the least electronegative. So there's nothing canceling out that charge. So therefore, you're going to get the polar molecule. Does that make sense? Okay, cool. Yeah, thank you for the question. So 3, draw the resonance structures for carbonate and find the bond order of each resonance structure. So if you remember from polyatomic naming, carbonate's 0, 3, 2 minus. So if we draw that structure, we get these three, right? So counting our valence electrons, we get 3 times 6, which is 18, plus 4, and then plus 2. So that would be 24 electrons total. So 2, 4, 6, we've used 6 electrons, we subtract 6. So we are left with what? 18? Okay, so go ahead and fill that out. 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 15, 16, 18, right? We have 18 here, but the thing is, notice how we ran out of electrons. So what we must have to do is we have to take this and make a double bond, like that. So drawing the resonance structures, we use these arrows to denote them, denote that they're resonating. So the one can go at the bottom, and then here, like that. And then we do C double bond O here. And so that's a 2 minus, and then that's a 2 minus, and that's a 2 minus. Okay, cool. And then so bond order is just shared atom, bonds over shared atoms. So 4 bonds, 2, 3, 4, and over 3. Yeah, that's a good point, Aishwarya. Like, linear molecules are nonpolar, but chemistry always has exceptions. So you kind of want to draw like the model out. Okay, cool. So we have the Lewis structure of SCN minus or CHEM. Which structure is the best Lewis structure and why? So with best Lewis structure problems, we kind of have to find the formal charge for all of them. Okay, so we're gonna do ahead and just find the group of S. So if you remember the formula, it's the group number minus the bonds minus the number of electrons. So it's 6 group number of S minus 2 bonds minus 4. And that's going to give you a 0 charge. Carbon is 4 minus 0, which is 0. Nitrogen is going to be 5 minus 2 minus 4, which is going to be -1. So we're going to have to do that for all of them. S is going to be, again, 6 minus 3 minus 2. That's just going to be a +1. The carbon is just going to be 4 minus 0, 0. Nitrogen is going to be 5 minus 6 minus 1, be -1. Sulfur, we repeat this again, 6 minus 1 minus 6 for 6 of these electrons, and then we do, that's a -1 charge. And then we do carbon, which is 4 minus 4, which is 0, and then you also subtract 0 because there's no 0. And then nitrogen is going to be 5 minus 3 minus 2, which is going to be 0. Okay, cool. So does anyone have any questions on how I got that math? Yeah, good point. I correct 5 minus 6 minus 1, that's going to be, yeah, so good math calculation. So my apologies. It's going to be -2. There we go. Make sure you kind of double check your math for this one. Okay, good catch, you all. So let's go ahead and kind of determine which one's the best formal charge. So I can kind of rule the second one out because it's kind of spread charge. The charges are too spread because there's a +1, a 0, and a -2. And we kind of want to try to narrow that down or kind of limit the charge spread. So we can go ahead and just not, we can say it's not this one. So it's not this one. And then for the first one, well, we both have -1 charge, and that's okay. Well, and that kind of makes sense because we have the SCN minus, it has a minus charge to it. So we're going to go ahead and check to see which one's the more electronegative. So if we're comparing the S molecule versus the N, right? We're going to notice that S is more electronegative than N in terms of electronegativity. So we want to put the charge on the -1 on the S. So that is going to be the best Lewis structure. Yeah, your formal charges also should add your formal charges across all elements should add up to the charge of the molecule. Yeah, that's good. It's a good thing to keep in mind. Okay, cool. So let's go ahead and kind of do this next problem. We have the structure for nitrite, which is NO2 minus. And two structures on the top of my head I can think of are this one and then that's one structure, but that can resonate and do this. And we can go ahead and kind of think of another one too. Instead of having we can also kind of do this structure. So we have one with double bonds and we have one with just single bonds. So if we go ahead and calculate the formal charge, we have -1 here, +1 here, and -1 here. That's from the formula. But for this one, we have 0, 0, -1, and then we have -1, 0, and 0. And that's by taking the valence electron group and then minus the number of electrons it has, minus the bond has. So if you notice, there are actually two good structures for this one. There's this one, and then there's this one. Why? Because they minimize the charge, unlike this one, which is like pretty sporadic. Okay, cool. So next question. So next is find the hybridization for at each indicated atom. How many sigma and pi bonds are in this molecule? So every time, like I mentioned in the review session, if you have a molecule like this, you want to go ahead and just draw all their hydrogens. So we have a hydrogen here, and notice how at each junction we need to have 4 bonds. So at this junction, there are already 2 bonds here, so we need to draw 2 more. And then right here, let's keep drawing them. And then let's see, that one already has one. That's 1, 2, 3, 4. That one has one. And then 1, 2, 3. We draw one here. And then 1, 2. Then 1. So we have 1 here, right? And then there's, for this carbon, there's 1, 2, 3, and then there's 4. And then there is here and here. Oh, I don't know how to differentiate between when it's so close. Oh, that's a good question. So if it's like that close, then I would say that the group trends always carry more value than the period trends. Because I think with across the group, you kind of change rings or change valence. So it would have a greater effect than versus a period, if that makes sense. Yeah, it depends. That's how I was kind of taught it, but I would definitely ask for your professor. But it's one of those like you have to kind of like look at the group trends trump the period trends, if that makes sense. Okay, cool. So with that being said, after we go ahead and do this, does that answer your question? I hope it does. If not, then let us know. Then we can kind of talk about it more. Okay, so we have oxygen 1, which is that guy, right? And so at first glance, you might think that this is sp3 hybridized because, you know, so that's the question is, oh, if this is sp3 hybridized or not. So let's go ahead and say that this is S. So I'm sorry. So this is S, and then P, right? And then there's also another bond here, which is P. So if you have something like this, you kind of want to make sure that if something can hybridize or not. So when we check for hybridization, you want to check for the second carbon, the carbon adjacent to it. So since this carbon is adjacent to it, it's sp. So let's see. So for that carbon, we have spp, and then we also have sp3. So that oxygen was sp3, and then this carbon down here was also sp3. Okay. So because they are because the adjacent carbon cannot resonate or it doesn't have that double bond, this one is sp3 hybridized. Okay. Cool. So the first N, it's going to be, you have a lone pair here, even if it's not shown. So, and you have a child bond here, so sp. So it's going to be sp. And then for the N2 right here, it's going to be sp, p, and then p. It's going to be sp3. Then you have C2, which is going to be SP and then P. So those are three groups. So just SPP. So just assign the labels. I think that's my best bet for you all. And so that carbon 3 has SP and then P. So it's SP2. And then for the sigma bonds, this is kind of a doozy. So I'll just give you all the answer. I counted 40 sigma bonds, and then I also counted 4 pi bonds. So we would have to count all the sigmas here, and then the single bonds, and then you have to count for the pi bonds. Because of the nature of this problem, I will go ahead and just recount it, and then send the final key to the SSC YouTube, where the materials will be uploaded. Okay, sorry about that, you all. My screen kind of flickered a little bit, but I should be back now, hopefully. Okay, I think I'm back, hopefully. Oh, okay, never mind.
If you're having trouble, like I could, I mean, I guess you're the one who's sharing, right? So
Yeah, give me 1 second.
okay, for number 5, let's see. That was, oh, the resonance structure one. So for that one, the best structure is we base that on formal charges, right? So we don't want to have, we want the negative formal charges to be on the most electronegative elements, which in this case would be oxygen. And we don't really want to have those negative charges on nitrogen. So therefore, the best formal structures would be the ones that place the negative formal charges on an oxygen and keep nitrogen neutral. Does that make sense? So in that case, it would be the one where nitrogen is double bonded to one oxygen and one oxygen is single bonded, and there is a lone pair on the nitrogen. And like there are two instances of that can occur because there are two oxygens. So there are two best structures for that. Does that make sense?
Okay, so sorry about the technical difficulties, you all. So what's going to happen for 7 is that the liver structures are shown, and we're asked to find the hybridization of each carbon, and then we're also asked to find the actual bond angle, and then the compound is the longest and the strongest. Okay, so we can just go ahead and get started on the hybridization. So for this one, we have this carbon, we have SPPP, SP3. For this carbon, we have, let me do that in different colors so that it's easier. SPPP, so it's SP3. And then we have, yeah, so both of these are SP3 hybridized. So for this carbon right here, we have SPP, that's Sp2. And then I can go ahead and do that in different colors so it's easier to differentiate. So that's SPP, Sp2. And then for the last one, we have SP, and then a different color, SP. So it's going to be both SP and SP. Okay, so find the actual bond angle for this one. So bond angle for 3 electron groups is 109.5 degrees. This one. So for this bond angle, you would expect it to be a little bit greater than 120 degrees because there's a double bond here, and this one would be a little bit less than 120. Why 120? Well, we have to account for the 3 electron groups, right? But it's going to be greater because of the double bond repulsion, and then it's going to be less than for here is because it has to make room for that double bond, so it takes more space. And for this one, just SP2 domains 180 degrees. Okay, so we found the hybridization, the actual bond angle. So which compound is the strongest? I mean, is the longest. So if you remember, usually the weaker one, the single bonds are the longest because it doesn't have that much energy attracted to it. So the single one would be compound A. And then the strongest one would be the one with the most bonds. Is going to be compound C because it has a triple bond. And this one would also be the shortest one. Also the shortest. Okay. Thank you all for coming to this review. If you have any questions, just let us know. But again, so really sorry for the difficulties and for the corrections. So I'll be sure to update the key and then upload it to the SSC website or the YouTube channel. Other than that, hope you'll have a good exam and good luck.